Okay, so now we're going to see this last solution, which is going to improve a little bit on the bounds that we got over here by Cormode and Muthukrishnan. So what we're going to see now is solution where, but before this, the space, the one we just saw, is 1/epsilon log squared of u. Now we're going to see one that is 1/epsilon log u. So we're going to get rid of one of these log u factors. The update time, we're also going to improve it by a log u factor, so now it's just all a log u. And finally, the query time is also going to be 1/epsilon log u. So shave another log u. Only downside is that now this is in expectation. So it's the expected query time instead of the worst case query time. So we're sacrificing a little bit there. Get an expected good performance instead of worst case, but we're going to improve everything by a log u factor otherwise. Okay. And again, the space here is optimal. The update time basically matches the CountMin sketch with just that element, and it's also close to optimal. And the query time here as well, there's 1/epsilon elements that we have to output close to basically. So this solution here, put it here, is something I did together with Larsen, Nguyen and Thorup. So let's see. It's super simple. Now that we've seen the other one, because all that we're going to do is that we're going to change all these error probabilities to put 1/4 in all of them except the bottom one, and then everything's the same. So we just said the failure probability for all the structures, all levels except the bottom one, just going to set them to 1/4. The bottom one is still going to be 1/u squared. There's very simple change to it. The update element is the same. The query element is the same. The only thing that's different is the analysis. Now and then we get expected query time instead of the worst case. So maybe we can start by just checking that we get that the space and the update time are what we claim they are. So this is not too hot. Space, well, we have one structure with a failure probability of 1/u squared, right? So that gives us a space usage of 1/epsilon log u for one of the CountMin structures. Then we have log u CountMin structures where the failure probability is a constant. Then the space is order 1/epsilon. So this is like a times 1/epsilon. So indeed, this is order 1/epsilon log u. We have log u cheap structures, one expensive. Similarly, with the update time, we have log u structures that are cheap, where the update time is constant. So that's just log u. And then we have one structure at the bottom level where the update time is log u. So log u plus log u, this order log u. If we get the claimed space and update time, the question is, what about the query time now? The expected query time and not the worst case query time. Okay. So let's see what has to change in this analysis, right? So before, the way we bounded the query time was to say, okay, we define these heavy nodes. The heavy nodes were those whose frequency was at least epsilon half times the 1 node, right? These were the heavy nodes. And then we argued that with high probability, we're never going to see a light node. So then the time was bounded by the time it took to visit all the heavy nodes. But now when we have a failure probability of 1/4, we probably cannot argue that we're never going to see a light node. It's too much to hope for. We'll probably see some light nodes. The problem is, let's say I'm kind of running this recursive procedure. I'm in some node I estimate the frequency of some element. Maybe this is light, but by accident, with probability 1/4, I'm going to visit. Then this node is again going to query two frequencies. They are also light, but I might make a mistake again and maybe recurse into these children. And then they might recurse into new children and new children and new children. So somehow it seems that this can branch in kind of crazy ways. So how can we argue that we're not going to visit very many nodes whenever we make a mistake, we have two new chances of making mistakes? This is what we have to try and count. I think there's a nice analogy. So this work was from before COVID, but maybe there's a nice way to try and understand it now, after having followed all the statistics when there was a pandemic. So I don't know if you remember, we had this idea of this infection number. I don't get what it's called in English, but how many people is everyone expected to infect? Like everyone who's infected, how many new people are they expected to infect with the disease? And we had this, if this R number was bigger than 1, then things were growing, right? We had this exponential growth in the pandemic, and it was less than 1, and everything dies out. It's a little bit the same. Every node that I visit, let's think of this as someone being infected. Every light node that I visit has two children, the two people it can infect, but it only infects any one of them with probability 1/4, the expected number of new people. This is similar to the pandemic. It's going to die out. This branching of new things that invoke new things is going to die out. And that's kind of the intuition for why it might work. We're not going to visit a whole lot of stuff. I think if the failure probability had been 2/3, then it would not work. But with the failure probability of 1/4, this will work. So let's try and. But now we have to prove it formally, of course. It's just kind of like a hand-wavy argument for why one would expect that this could work. Let's try and try to prove it. So we're still going to define heavy nodes and light nodes like before. Node is heavy again. Nodes, light in red. The red one's heavy. If its frequency, let me again, like F, I, J is the frequency of node B. The sum of everything in the subtree is at least epsilon half times the 1. So this is a heavy node, and otherwise it's light. We already argued that the number of heavy nodes in any level is less than or equal to 2 over epsilon. This is just by definition. There can only be 2 over epsilon heavy nodes in the level, just because the 1 norm of the level is equal to the 1 norm of full frequency vectors. There cannot be too many heavy. So we can start by bounding the time spent visiting heavy node. Right? So for the heavy nodes, whenever I visit a heavy node, I'm going to make two estimates of its structure. If my heavy node is sitting level 1, it's going to be expensive because I'm using the CountMin structure with a failure probability of 1 over u squared. I'm using a very accurate CountMin structure. So the heavy nodes in level 1, but there are only 2 over epsilon of them. Right? So the heavy nodes in level 1, visiting them is going to cost me only this 2 over epsilon of them, and they cost log u each. And then there's all the heavy nodes in levels above, but for those heavy nodes, querying the CountMin structure has a failure probability of 1/4, so the query time is constant. Like there are 2 rows in these sketches. Log 2 of 1/4 is we just have the log 2 of 4 is 2, so there's only 2 rows in these things. So there are going to be in log u levels. There's going to be 2 over epsilon nodes, 1 over epsilon, that cost a constant to query, right? So the total time for visiting all the heavy nodes is, as we want, 1 over epsilon log u. So visiting the heavy nodes is fine. Now we have to bound the contribution to the query time from visiting the light nodes. Right? These are the only ones we really care about, all the light nodes. how much are we paying for the light. And we're going to split that analysis into two. We're going to look at the contribution from light nodes in levels 2 and up. And because they are cheaper, they cost constant each. And then we're going to look at the contribution from light nodes in level 1. They are more expensive. They cost log U each. Right? We want now to bound the. Maybe we want to know how many light nodes visit from level 2 and above. That's what we have to bound, right? Because that's the contribution to the runtime is proportional to this. So x, let's just define a random variable. X is the number of light nodes we visit in levels 2 and up. So maybe let's define xv. For a light node v is an indicator that is 1 if visit 0 otherwise. Right? And then the thing we want to bound is the sum in of v such that v is light. And maybe let's say level v is greater than or equal to 2, and then xv. Make sense? This is just counting how many light nodes we visit in levels 2 and above. We want to bound the expected query time, bound the expected value of x. Expected number of light nodes C in levels 2 and above. Down. Erase this definition here. So, expectation of x. What do we do first when x is a sum of variables? Use linearity of expectation. Yes, yeah. We're going to use linearity of expectation, right, to write this as sum of all these v are the light nodes of level 2 and up. Expectation of xv. And indeed, these xv's are these nice indicator random variables, so the expectation. Probability v is visited. Probability visit v. Okay. So far, so good. But now we have to do something special to analyze these. We have to be a little careful because there are many nodes that are light in this tree. Like there's like proportion to the universe size light nodes. And we know that these estimates in the CountMin structure, they fail with probability 1/4. And we don't want to argue that we have to visit a quarter of, we don't want to just put a quarter here on all the nodes in the universe because then we've got to visit u quarters. Next. We just said put it in 1/4 here and sum over all the light nodes of the entire tree. We're going to get something that's way too high. We're going to get u over 4. We have to be more clever in how we analyze it. And so for this, we need a definition here. So let's look at a light node V sitting somewhere in this tree. And let's follow the heavy nodes. This, maybe these are the heavy nodes. Remember, heavy nodes are the ones whose frequency is at least epsilon half times the 1 norm. Now V is sitting somewhere in this tree. Now we define the light depth of V. Let's call it d of V. The light depth, it's the number of steps up to its nearest heavy ancestor. Okay, so this light depth here is 2. This node would have a light depth of 1. This one of these will have light depths of 3, and so on. And so let's define the light depth of V as the distance to the nearest heavy ancestor. And now let's define, let's just call it Li is the set of V, so that B is light, the light depth of B is I, and the level of B is at least 2. We can partition our B's into these sets depending on their light depth. Makes sense? Just going to take all the light nodes in the tree and I partition them into a bunch of sets depending on its light depth. Now I can write this sum up here as sum. What can a light depth be? It could be anything from 1 to, I guess, log u minus 1 is the highest light depth, I think. Maybe log u. Let's just do log u to be safe. And then I'm going to say, I'm going to sum over all the v in Li. Then I'm going to do probability visit v. I'm just going to split the sum into this. I'm going to sum over all these sets. And now, let's say I have a particular node B whose light depth is some I. What can I say about probability that my query procedure down here is going to visit B? I want to argue this probability is small, right? I want to say it's unlikely that I get to visit B. What has to go wrong for me to visit? Yeah?
You have to fail the light depth.
That's exactly right. I have to fail the light depth amount of times, right? Because if I am to visit V, it must have been the case that at some point I was in the nearest heavy ancestor. Then I queried the first node on the path down to V. This node is light because of the light depth. This node is light, which means I would have to fail in order to visit it. And I must have overestimated it by way too much. And this estimation was done in some CountMin structure corresponding to this level. Then I must have also been in this node and estimated down here and failed again. And this is a different CountMin structure than before. And I have to do this, the light depth of V, many times that I have to fail. And now the really nice thing is that if we initialize these CountMin structures with independent hash functions, independent randomness for their random seeds, then these failures are independent. Right? So which means the probability that I fail I times, what can we bound that by?
1/4 to the I.
1/4 to the I, right? Because they're independent, all these structures, and we have to fail in all of them. So this is bound by 4 to the minus I. Now we have the sum from 1 log u. Sum over b in Li, 4 to the minus I. And here it's important that all these estimates are to different CountMin structures, different levels, so that they're independent. If I ask the probability of failing in both of these two estimates, this is no longer independent. If I take two neighboring nodes in the same level, right? So that's to the same CountMin structure, then we don't have independence in the failures. But because they're different levels, these failures, it's different structures with their own independent randomness. These failure events are independent. So we get this 4 to the minus I. And now, of course, this is a sum from 1 to log u, size of Li, 4 to the minus I. Next thing, we need to bound how many nodes can have a light depth of I. This is actually not so easy to count. You need to be a little careful. So how many nodes can have a light depth of I? So I'm going to count it in a kind of a funny way, in a kind of reverse way. So for a node to have a light depth of I, its nearest heavy ancestor must be I levels up. Make sense? So this is kind of like this node here. You can kind of say this node here is responsible for that node there. So if we take a heavy node like this one, how many light nodes of depth I can it create? Right? How many light nodes of depth I, where I am the nearest heavy ancestor? So how many can it create? I have one fixed heavy node. For how many light nodes that have light depth I can I be the nearest heavy ancestor? How many nodes like V can sit in depth I below me? Yeah, 2 to the I, right? Because it's a binary tree. So any heavy node can construct at most 2 to the I descendants of like depth I. So, okay, so we now know that this size of Li here is less than or equal to 2 to the I times the number of heavy nodes in the entire tree, right? In levels 3 or 2. So that is, and we already said there's at most 2 O epsilon heavy nodes in one level. So there's like 2 O epsilon log U levels at most, 2 O epsilon log U heavy nodes in total, each of them creating 2 to the I light nodes at depth I at most, and the failure probability was 4 to the minus I. So these two are now, this is what we started out in the beginning. This is kind of the infection rate and how many you infect, right? It's 2 and it's 1/4 here. Because now if we bring these two together, right, and move the 2 OFs log U outside, then we have the sum onto log U of, well, 2 over 4 to the I, so that's 1 over 2. This is the sum of a quarter, a half plus a quarter plus an eighth. So this sum is at most 1. So we have just shown that the expected number of light nodes that we visit is at most 2 over epsilon log U. Basically because this branching out dies more quickly than the branching factor. Because we kill them with probability. They only continue with probability 1/4, and there's only 2 neighbors out every time. But the key to analyzing it, which I think is kind of slick, was this light depth. You're trying to define this light depth and then notice that you have to do independent failures across the levels when you get down to this. So the expected number of light nodes that we visit is at most 2 epsilon log U in these levels. All of them requires us to do 2 CountMin estimates, but on a structure that has constant time varies, right? Because we only had a failure probability of a quarter, so the estimation time is constant. Right, so this gives us 1 epsilon log U time. So the only thing we haven't done yet is argue about the cost of the light nodes sitting in level 1, because they are more expensive, because they have to query this expensive node. So let's just do that one. We're going to do something very similar. Get rid of this. So now, so let's just say now I'm going to write it out. The light and level of, these are the ones that we're missing. We're going to do the same split based on these light. We're going to partition them into the light depth again, because this was a good idea. We use that. So this is what is sum over the different values of the light depth, sum over now we change this definition. So we're now looking only at the nodes in level 1. Step. So now I'm going to do V and Li. And the probability that we visit this node was 4 to the minus I by the same arguments. Light depth is I. The chance that we visit it is the most 4 to the minus I. And so this is, of course, again, size of I, 4 to the minus I. Now it's just that now we know that the level is 1, so this might help us to argue that the size is a little bit smaller. So in particular, the observation now is that if I have a light depth of I, and I am sitting in level 1, where's my nearest heavy ancestor sitting? What can I say something about the level? If my light depth is I, and I'm in level 1, what level is my nearest heavy ancestor sitting in? Level I plus 1, yes, that's enough by 1, I think. Yes, in level I plus 1. Does it make sense? It has to be I levels above, so it will be in it has to be in level I plus 1, my nearest heavy ancestor. Which means that the only heavy nodes that can create nodes of light depth I in this level 1, they have to sit in level I plus 1, and there are only 2 over epsilon of them. And that's the difference. There's only 2 over epsilon nodes that can be heavy in level I plus 1. So, and each of them can create 2 to the I many descendants in level 1 that are light. So therefore, now there's only 2 to the epsilon times the I. Basically, because now we're using, they have to sit in level I, or they could sit everywhere. So this is why we're going to shave a log u back. All right, so now we can move the 2 over epsilon out. And again, it's a sum from 1 of u and 1 over 2 to the I. And this again. So the expected number of light nodes in level 1 that we visit is most 2 over epsilon. And they cost log u each. That's 2 over epsilon log u contribution to query time, which is also what we were aiming for. So it also fits here. I think actually we forgot to argue about the correctness when we started out. I only said that the query time was fine. But the correctness proof is simple, we already did it. If you remember, how did the correctness proof go? The correctness proof, we only looked at the bottom level. And we said, we defined these events that argued the CountMin index at level 0 overestimated this node, right? So maybe we can just write it up again. For the correctness, right, we define these. We could define these events for every light node in level 0. We can define this event at a CountMin of 0, that estimate of this, maybe I is greater than true frequency plus epsilon half times 1. This is how then we add that this event has to happen for us to accidentally put I into the output list. And so we can easily do like the same analysis where we just union bound over all these events, because we didn't change the CountMin level 0. We kept it the same. So we can use the same analysis. CountMin level 0 still has this tiny failure probability, so we can just reuse the same analysis. That's fine. It's just the same. Okay. So I think we went through it all, and now maybe let me just spend the last bit of time just talk about some possible extensions that we're not gonna cover. And but that's it. That's basically the state of the art of these runtimes here. So, okay, so now I deleted the heavy hitters problem. So of course you could ask yourself, what about the general turnstile setup, right? So what happens if I want to do heavy hitters? General turnstiles, so I can also have negative frequencies. So let me just tell you what's known and what makes it difficult. But we're not going to do it. I can just kind of give some hints. So epsilon heavy hitters, but general turnstile. So typically, if you look at this one, you're going to look at this L2 version instead. If you remember from last time, we saw this count sketch that could also that worked in the general turnstile model, where you estimate frequencies and then your errors are with respect to this 2 norm of f instead of the 1 norm of f. I hope you remember this one. But there's a different version what you want to produce L such that every I such that Fi is greater than epsilon times 2 norm is an L, and no I such that frequency of I is less than epsilon half times 2 norm is L. So this is typically the version you look at if you want to do general turnstile. Here one can show that the size of the output is as large as 1 reference squared. But what are the difficulties that kind of arise, right? So the natural thing would be try to repeat something with this tree, right? Similar to here, to find things quickly, but use this count sketch instead of the CountMin. Right? We saw this count sketch that could estimate frequencies with errors proportional to this 2 norm instead of 1 norm. But there are a couple of things that break down. And let me try and sketch. So in particular, we used quite heavily that in this tree. So now let's say the natural thing would be, let's build a count sketch on every level. Count sketch to represent levels. Several problems arise. One of them is when I sum up the frequencies from the level below into this frequency vector, the norm does not stay the same. 2 norm. Right? Because let's say all my frequencies are 1. Then at the bottom level, my 2 norm, if you remember right, the 2 norm is the square root of the sum of the squares of the frequencies. So in the bottom level here, let's say here it's square root of 8. On the next level, if I sum things up, it's 2, 2, 2. So then it's gonna be square root of, well, 2 squared is 4, and 4 is 16. So it's a bigger 2 norm in the level above, right? When the 2 norms go up, and remember the count sketches, the errors they make are proportional to epsilon times the 2 norm of the vector they're representing. So that's bad when we get up high, right? If these 2 norms grow and grow and grow, then we're in trouble when we get to the top of this thing. So that's one thing that kind of breaks in trying to do it. What you can do instead, and this requires some work, is to say, instead of summing things up in every level, I do like this count sketch, and I have a random hash function G that maps the universe. So let me write here GI, kind of maps the universe to random signs. And then I'm gonna add them up, but where I hash them, so I'm not gonna add them up, but I'm gonna add them up with this sign multiplied onto their values. Okay, so that can kind of fix it. Turns out you need these hash functions to be 4-wise independent, not just 2-wise independent. That will ensure that these the 2 norms are going to stay close for probability, so and still use estimates. So that's one thing that makes it worse. Then you have this recursive query procedure over here. One new problem that also arises is that the count sketch doesn't always overestimate, it can both overestimate and underestimate. So which means we might actually risk that we're not going to reach the heavy elements in the leaves. And before we always reach them because everything on the path is heavy. Now we might risk them. Also because we're summing things, again, also we're summing things up with these random signs as well, so that also causes trouble in risking that things on the path don't look heavy, so we want to have to deal with that as well. One can take this kind of this solution up here, the kind of slow one, where all the failure probabilities are tiny, 1 over u squared. That one you can actually use some modification and then define events for every node of the tree saying, I will follow all the heavy nodes, I will never visit a light node. You can do those 2 things. That kind of works, giving you these log squares. Like the first kind of slow solution gives you the log squares. The real issue is that if you try to do what we did and set this probability to a quarter, then you lose because you're not going to follow the paths down to the heavy nodes. Right? Because with a probability a quarter, you're going to stop on your way down. Already the first time, right? You have to get all the way down. So that breaks completely. So our improvement is just out the window in that setup. And actually, this log u squared was the best solution in a long time. If you read this paper here, I guess if we go to this L2 version, these become squares, and they have to be because the output size can be up to 1 epsilon squared. So we give a solution where this is 1 plus little of 1, or something like this, in the paper. So we improve it from a log squared to something that's basically log u and some, I think it's probably log u. But that is nowhere near as clean as this solution here. That is like some 30, 40 pages of all sorts of stuff with error correcting codes and expander graphs and clustering algorithms, all sorts of stuff to make this work. So it's extremely impractical, but theoretically it's great. Right? But you'll never implement it in practice. I think some of the constants in there is like 1 million or something, and you're going to shave a log u. It's purely theoretical. Whereas this one is super practical. The first one here, the constant, right? That works super well in practice. This one is only for the theory, but it's interesting. I think there are many nice ideas in it, but it's much more fun. I guess that was just some extra pointers to what else you can do in this heavy hitters, but I guess there still remains to be developed like a clean and very simple solution that gets. Yeah, I think that's it for today.